In today's lesson, we are going to be looking at completing the square. So this is a method that will be important, especially when we're dealing with trying to solve quadratics or find certain pieces of information about quadratics. So just a quick little discussion, something to think about. If we're converting from standard form to vertex form, so standard form, y equals ax squared plus bx plus c, and vertex form is y equals a times x minus h squared plus k. So why would we want to convert to vertex form? Why would I want to go from standard form to vertex form? What benefits do I get from dealing with vertex form? Well, our vertex form tells us the vertex, and by telling us the vertex, it does tell us the axis of symmetry, and it tells us the max or minimum value, or we sometimes call it the optimal value. It tells us transformations. It does tell us our step pattern and the direction of opening, things like that, but we get that in our standard form as well because the A values happen to be the same. But other than that, there's not really much else that the standard form gives us, except for maybe the y-intercept, which I can easily calculate using the vertex form anyways. So I usually want to convert to the vertex form because it is, or it does give us more pieces of information, and specifically, it does give us this optimal value, right? If we're trying to optimize something or we're trying to find an optimal value, that's usually what we're looking for, right? We want to usually know what is the highest, what is the lowest for whatever our situation or scenario happens to be, right? What's the highest the plane will fly? What's the maximum profit? What's the minimum amount of material? Right, things like that. We want to know the optimal value. So that's why we'd want to convert to vertex form from standard form. And the method that we're going to be using is called completing the square. So if you want, there is a nice YouTube video. Just Google or just search completing the square demo, and we'll kind of see an example with algebra tiles, how to do that. I'll be going through an example as well for ourselves, showing us how to do that. Right, so I have the expression or the quadratic formula in standard form, x squared plus 4x plus 4. Right, and I want to basically convert this into a perfect square. So if I bring up my algebra tiles, I want to have x squared plus 4x plus 4. So an x squared would be one of the large shapes. I have the 4x's. So I'm going to have 1, 2, 3, 4. And I'm going to have 4 ones, 1, 2, 3, 4. So the idea of completing a square is going to be, I want to make a square out of all of these shapes and then look for the dimensions. So in this case, if I'm going to do that, I'm going to put these two together like this. These two I'm going to rotate, make them the horizontal version, and put them in here. And now I'm going to take my ones place them in like such, and now I have a square. Right now I have a square that has the dimensions x plus 2 and x plus 2. So I've created a square from the trinomial values, or from the terms in the trinomial. So that means this expression expressed as a perfect square, this quadratic expression as a perfect square, is x plus 2 times x plus 2, or I can just say x plus 2 squared. I'll come back to it now. Now, if this is a quadratic expression and I set y equals, I've now gone from a standard form kind of to a factored form, and now to a vertex form. Right? I don't have an A value. I have my H, and I have my K at the end. Even though we don't see anything, we can assume it's plus 0. Right? So that's how we're going to use a perfect square to help us write it in vertex form. Right? Because a perfect square trinomial, or the factored version of a perfect square, is kind of like a vertex form equation. Now, if I look at the next one, x squared plus 6x plus 5 is not a perfect square. So now, how are we going to rewrite, or how are we going to convert this? How are we going to convert this into a perfect square trinomial, or a perfect square? So let's go back to our shapes here. So I'm going to get rid of these shapes. I'm going to pull out the shapes that I need. So I need an x squared. I need 6 x's. So 1, 2, 3. Because it's even, I'm probably going to have 3 that are the other way. 1, 2, 3. And then plus 5. 1, 2, 3, 4, 5. So now I'm going to still use these shapes to try to make a perfect square. So let's say I'm going to move my 3 here. I'm going to put another 3 on the top. I'm going to take these 5 and order them to fill in these kind of spots here. Now those are all the pieces I have. Now, if this was to be a perfect square, what would the dimensions be? Well, I'd have an x plus 3 and an x plus 3 along the top. So I'm going to write that out for right now. So x plus 3 times x plus 3. So it'd be squared if it was a perfect square. However, I am missing 1, 2, 3, 4. Right? I'm going to use blue ones as just kind of placeholders here. So I'm missing 1, 2, 3, 4 values that I'm missing that would make it a perfect square. So it's not really a full perfect square. It's x plus 3 squared, but minus 4. Because there are 4 pieces missing from that perfect square. So if I remove those out of the way, let's go back to our slides. So if I have this now as my expression, x plus 3 squared minus 4, because I didn't have 4 pieces, this still looks like a vertex form. Right? If I put y equals, I still have my a value, I have an h, and now I have a k. So even though it doesn't quite make a perfect square, right, it still gives me a vertex form equation. So we're still going to try to complete the square, and just if we don't happen to have a perfect square, then that's fine. Whatever's left over, or kind of the difference, or the extra, will be our k value. So let's look at another example where, again, it's not going to be a perfect square. But let's go through and use the algebra tiles to see what we can come up with. So I'm going to remove all of the ones that I used. So I'm going to bring out my x squared again. I'm going to have 4 x's. So kind of in the pattern we're going with, I'm going to have 4 x's. So there's 2, 3, 4, trying to balance it out on either side because I'm trying to make a perfect square. And now I have 7 ones. So 1, 2, 3, 4. Okay, there's my perfect square, x plus 2 by x plus 2. But if I look at my tiles, I'm still missing 3 tiles. So I'm going to have to add in 1, 2, 3 little squares. So now I have all my tiles here. So If I wanted to express this trinomial, the x squared plus 4x plus 7, as a perfect square or with a perfect square, it would be the x plus 2 times x plus 2, or x plus 2 squared. So let's go, so we'll say x plus 2 times x plus 2, right, for our dimensions. And then we have our 3 leftover pieces, or plus 3. If I want to rewrite this, x plus 2 squared plus 3. So let's go back to our slides. So again, we still have something that looks like vertex form, even without having, even with having more tiles than necessary to make a perfect square. We can still write an expression involving that perfect square and creating an equation that is in vertex form. We have an a value, we have our h value, and we have our k value. So we can use algebra tiles to kind of complete the square to turn a standard form equation into vertex form. Now, we're not always going to have algebra tiles with us, or sometimes maybe even though we're visualizing it, maybe some people find this more difficult and they prefer something more, we'll say, analytical or logical in a way that it's a step-by-step process, or algebraic. So this is our next method where we're going to use algebra. So we're going to use algebra to help us complete the square or convert our standard form to vertex form. So we're going to use what is called completing the square. So it's going to be the algebraic version of what we were doing with the tiles. So we have our equation in standard form. Let's write it in standard form just so we know. And I want to write it in vertex form. So we have some steps on the side to help us. So the first step says group the first two terms in brackets. So y equals x squared plus 8x in brackets, and then plus 5. It says to make a perfect square inside the bracket, divide your b value by 2 and then square that number. So this is what I call the magic number. So we're trying to find a number that makes this bracket a perfect square. And what we're going to do, or how we're going to do that, is we are going to take this b value, or 8, divide it by 2, and then square it. Or, in other words, 4 squared, which is 16. So our magic number that will make that bracket a perfect square is 16. So I need to put 16 into that bracket. So y equals x squared plus 8x plus 16. However, the second part of that step says we must add and subtract this value, because we need to keep things balanced. If I add 16 and I minus 16, technically I haven't changed anything. I haven't changed it. If you add 16 and take away 16, they cancel each other out. So I haven't done anything. That's still going to be in the bracket. And then I'm going to have my plus 5 still. So I haven't changed anything yet to my equation, right? If I look at the numbers, nothing's really changed. Right? Yes, I have 2 new values, but I've added it and I've subtracted it. They cancel each other out. We're not going to cancel them out though, because the next step said is to take your negative value outside of the brackets. So that means that this minus 16 is going to now move on the outside of the bracket, and I'm going to collect it with the 5. So I'm going to have x squared plus 8x plus 16 plus 5 minus 16. Now this bracket should be a perfect square trinomial. By adding that magic number, that 16, that is going to make it a perfect square trinomial. So as long as I put in the right number and follow that second step, that bracket is going to be a perfect square trinomial. So that means I can do x plus 4 squared, right? So I could factor it. It could do it the long way, but I know it's going to match, or it's going to be a perfect square because of that value I added. So the square root of the first term, square root of the last term, and then the sign from the first between the first two. And then I can simplify that outside, plus 5 minus 16. So I get minus 11. And now I have an equation in vertex form. So say therefore y equals x plus 4 squared minus 11. So now I have my vertex form, and I started with standard form. So this is how we algebraically complete the square to convert between the two different forms. Now, one thing to note, it does get more complicated, right? In more complicated problems, you may have to multiply this value by your a value, right? As we go through some of these examples. So we will come across an example where we might have an a value, but this example here, we had an a value that was 1. So we didn't have to worry about it. Let's do the same thing with the next one. We're going to go through the same steps, right? We're going to complete the square. So the first step said, let's put brackets around the first two terms. The next step said, I need to find a value that makes the bracket a perfect square, or what I'm calling our magic number. So I'm taking that b value, that second value in the bracket, I'm dividing it by 2, and then I'm squaring it. 6 divided by 2 is 3, and then I'm still squaring it, or 9. Once I find that magic number, that value, I'm going to add it and subtract it inside the bracket. The next step says I do have to move that negative value, the negative magic number, out. So I get y equals x squared plus 6x plus 9 minus 11 minus 9. Now that bracket is going to be a perfect square trinomial. So x and 3, so the square root of the first term, square root of the last term, the sign between the first two, so x plus 3 squared, oops, not cubed, x plus 3 squared, and then minus 11 minus 9, I get minus 20. Double check something, just want to make sure. Yep, just wanted to make sure I did my adding right with the last one. But now I have the vertex form from standard form. So again, this is a new process. It's new steps. So you do need to practice this so that you are comfortable going through these steps. Now, what happens when a does not equal 0? Right? So what happens when a does not equal 0? Or does not equal 1, sorry. Right? So for example, we want to find the max or min point of the parabola. And the parabola is y equals 2x squared plus 12x plus 11. So if I go through, I'm going to go through the same steps. There's going to be one extra step. So I'm going to put brackets around the first two terms. X squared, or 2x squared plus 12x plus 11. Now, the new step, before we go any further, we need to factor the coefficient if I knew how to spell coefficient. we're going to factor the coefficient. Or factor the coefficient in front of the x squared. So the value that is in front of the x squared, in this case 2, we're going to factor that out. I'm going to factor it out of the bracket, so what that means is I'm going to be left with 2, and then inside the bracket, x squared plus 6x. So I'm only factoring the coefficient out that's in front of the x squared. So I'm factoring it's kind of like a version of common factoring those first two terms. The plus 11 is still there. And now I'm going to go through the next step that I've done previously. So I'm going to find my magic number. So to find my magic number, I take that second value, that's 6, divide it by 2, and then square it, or 3 squared, or 9. So now I'm going to have, again, following the same steps. So I have had one new step. Everything else right now is going to be the same. X squared plus 6x plus 9 minus 9 plus 11. That minus 9 is going to move on the outside. However, because this entire bracket, right, this bracket, everything inside the bracket is being multiplied by a factor of 2, if I move something outside of that bracket, I need to reapply that factor. So another step that's different is we need to reapply the factor to the negative value. So I'm just going to color code it. I'm going to put a star there to show that when I move that negative 9 out, I have to reapply that factor to that negative value. So that means I have y equals 2 times x squared plus 6x plus 9 plus 11 minus, and I'll write it out a little bit longer. You don't have to show this in between step, but minus 9 times 2. So I'm reapplying that factor of 2, that a value. You don't need to show this step. You can just go through and do that step, that multiplication before and write it down after. So you could just jump to this step, which would be 2x squared plus 6x plus 9 plus 11 minus 18. So you could jump to that step from up here if you really wanted to. I'm just kind of showing you step by step. So now everything in the bracket should be a perfect square. So the square root of the first term, the square root of the last term, the sign in between the first two terms, squared, and then I can simplify plus 11 minus 18 is minus 7, and now I have the vertex form. From that vertex form, I can find my max or minimum. In this case, because it opens up, it means therefore there is a max or a minimum of -7. So just the y value of the vertex. So that means it opens up. We have our vertex here of -3, -7, and the minimum value is the y value specifically. So it is the minimum of -7. And this is how you would complete the square for a standard form quadratic that has an a value other than 1. So a few extra steps, right? But the same general idea.